In this lecture, we're going to change topics from energetics and start thinking about something called functional groups. This is really going to lead into the rest of the next 2 semesters. The first discussion, though, is going to be on one of the more important functional groups. But before we get into it, let's define what I'm talking about here. So I keep saying this term, functional groups. So this is really a major focus of organic chemistry. So functional groups are sort of a regular pattern or arrangement of atoms with predictable properties. Okay, so these regular arrangements of atoms with predictable properties, by studying functional groups, we can understand various kind of collections of molecules' properties without having to memorize each individual molecule's properties, which is great. So these allow us to know a lot of properties about a lot of molecules without having to memorize so much information about each molecule. Okay, so that's a lot of words. Basically what I'm saying is that this will make our lives easier. The more we kind of approach organic chemistry, not as this collection or this way of thinking about millions and millions of molecules individually, rather we think about and kind of stereotype a bunch of classes of molecules. So for example, molecules that all look like ethanol, for example, which is the active ingredient in alcoholic beverages, molecules that look like ethanol we would call alcohols. So that's one class of molecules, that's one functional group. There are also other molecules I keep seeing in the diet craze, that sort of thing, called ketones. There are acids or carboxylic acids, amines, amides or amides, depending on what part of the world you are talking, where you're at in the world when you pronounce that word. There's peptides. They are essentially the same thing as amides. And then what we're going to talk about today are alkanes. And alkanes will be the only functional group that we discuss for the next few exams, next few learning modules, I guess. It's just a really good foundational functional group. So, as I kind of just mentioned, alkanes are going to be our first functional group. Okay, and alkanes are a family of molecules. They're a functional group. They're a family of molecules with only carbon and hydrogen atoms. So there's a few rules to be an alkane. We only have CH atoms, and as a result, these fall into the category of molecules called hydrocarbons. Hydrocarbons are not a functional group, but they're just molecules that only have carbon and hydrogen. Okay, so they only have C and H atoms, and they only have sigma bonds. That is to say, we're not going to have no, double and triple bonds. No double and triple bonds, just sigma bonds. All single bonds are sigma bonds. And then lastly, it's not really, this third one isn't that big of a, I mean, it's fairly obvious given the first one, but we must have at least one carbon atom. At least one carbon atom. I'm going to make that nicer. I'm just writing the same thing. At least one carbon atom. It's important enough to mention. Okay. With this in mind, before we break into some of the properties of alkanes, let's try to practice this a little bit. Is it an alkane? So is it an alkane? Okay, is it an alkane? We can actually go through and label these. I'm going to give you a second to give it a shot. So to be an alkane, we need only carbon and hydrogen atoms. So it's going to rule out this one and this one. And we need only sigma bonds. So no carbon hydrogen, excuse me, no carbon carbon double bonds, or any double bonds for that matter. So that's going to rule out this one. And we need at least one carbon atom. I'm adding one in here. H2, for example, is not an alkane. That leaves us with yes for this first one, second one, third one. Okay, so hopefully that was helpful just to kind of see the rules in light of a few examples. Okay, so now let's get into some of the properties of these things. And these things are actually all the rage right now. Alkanes are. They're in the news quite a bit. Not with good press, though, and for good reason. It's a good reason that we're paying attention to these things. That doesn't mean they're not worth studying, but and knowing about, certainly I think that's very important. It's just that as we're becoming aware of the consequences, well, let's get into it. You'll see what I mean. Alkanes are the main class of fossil fuels. Okay, so they're the main class of fossil fuels, and as a result, these things are commonly used for their combustion properties. And combustion, let's not demonize this too much. Combustion, fire, is an incredible chemical process and is incredibly useful for the energy output that it provides. Now, what we've done is we've over-engineered the use of combustion, I would argue, and it's causing problems, especially for us environmentally, because our planet is not meant to sustain as much carbon dioxide as we have. And as we're kind of at the rates we're getting at, we're just not meant to sustain life with that much carbon dioxide. And hydrocarbons are a nice way of storing, alkanes are a nice way of storing carbon dioxide, but we burn them. So they're commonly used for combustion. This releases a lot of CO2. And any molecule with 3 or more atoms can induce the greenhouse effect if it's in the gaseous state. And so if you have 3 atoms or more and you are a gas, then you are a greenhouse gas. 3 atoms or more as a gas, doesn't that mean that water that's up in the sky, you know, moisture, that sort of thing, humidity, is a greenhouse gas? Absolutely. But we have a water cycle. If we get too much water, it rains. If we get too much carbon dioxide, it does not rain carbon dioxide. That would be amazing though. It would taste like kind of soda all day. I think I've mentioned that in a previous lecture. Okay, I've done so many of these videos. Anyway, so it releases a lot of CO2. There is a catch though. When looking at things to burn, before we knew that we could run out of this stuff and that it would cause too much CO2, I'm just going to be honest with you. Alkanes burn very cleanly. There's a cool experiment that we used to do, but it required use of some toxic chemicals, where I would take a beaker of an alkane and a beaker of something with a lot of double bonds, but was otherwise just a hydrocarbon. They would be isomeric of each other. And the molecules would, well, not perfectly isomeric as we get to the definition of that, but I would take both of these molecules. This is hexane, and hexane is like octane. And this is benzene. The difference is benzene is a ring and it has carbon-carbon double bonds. And if you burn this, if you burn benzene, it burns and makes ash and soot. It was really gross when we burnt it. So I just pour a little bit in kind of an evaporating dish and throw a match in, and we'd watch it burn, and it would be disgusting, and it would stain the hood black, and we'd all feel bad that we lit it on fire. Whereas octane, it did not produce smoke, and this one made smoke, whereas benzene made smoke. Hexane did not produce smoke, ash, or soot. We dropped a match into this dish with clear liquid, and we would see a flame, but there would be no smoke above the flame. And when it was done burning, the evaporating dish would be clean. It wouldn't leave behind any ash or soot or dirt. So you can imagine, if you have an automobile, how annoying it would be if you put in a molecule that was flammable. Both of these molecules are flammable, but if you put in benzene and you said, hey, benzene is flammable, so I can let my fuel injector do its thing, your car would be spewing out smoke and your fuel system would be covered in soot during the course of the internal combustion engine doing its thing. So really important that you burn things that burn cleanly for the sake of the environment. Now, again, the CO2 issue, as we're realizing, and the scarcity of hydrocarbons, as they are fossil fuels, makes this problematic and not sustainable for long-term use. But let's not forget that our discovery that these things burnt cleanly was a big discovery for us in terms of advancing the automotive industry. Okay, I guess I should highlight this too. Okay, so they burn cleanly. So those are the sort of main properties, I guess, that we're going to look at for a while. But another thing that these molecules do, it's not really a property, it's just a nature of how these things are defined, is alkanes form the backbone or parent structure of most organic molecules. And that's going to get into this idea of the fundamental hydrocarbons. This is going to be a longer list, so get a new page out. So the fundamental hydrocarbons, and I'm just going to be honest with you. You got to know this. I mean, and it's not just for like a test. You got to know these for like your chemical career. So definitely, if you want to do anything with chemistry, you have to know this. If you want to do anything with molecules of biology or physics, you should know these. So memorize this. It's really helpful. Okay, so what we have here are a few things. We have a name, a number of C's, carbon atoms, and then a structure. Okay, it turns out the structure might seem like the most overwhelming, but it's actually not. It's the name and tying that to the number of carbon atoms that is very less intuitive to learn, but is important to learn. So how this goes is we first have methane. I start with methane. Everybody's probably heard of it for cow farts and that sort of thing. It turns out it is an issue with cow farts, but it's also a really potent greenhouse gas, worse than CO2. But methane has one carbon atom, and all of these are alkanes, I should add. That's important if we know the number of carbon atoms and we know that they are all alkanes, we can write the structure. So if we're going to have, if we're going to have an alkane with one carbon atom, we are going to call, this is going to be the structure, CH4. So I have methane with one carbon atom, and this is sort of the, well, you'll see in a second. So it's better with this structure. So here is, the next one is going to be ethane. Ethane has two carbons, and we're just going to go and make a list down to 10 probably. 3, 4, 5, 6, 7, 8, just so you can see where we're going. 9, 10. Okay, so ethane has a structure. There's a way to make it gray here. So ethane has a structure of, oop, goodness, screw that up. And it's C2H6. So there's the structure, it's just one line. It's a bond line structure. So it's one line connecting two carbon atoms together. So ethane is the first example where we can see the utility of knowing these things. If I show you, I'm just going to write it in red here, then I'm going to erase it. This molecule is an alcohol. The structure is an alcohol, and it has the name ethanol. Ethanol sounds like ethane, but it's got the anol suffix to it, so it sounds like an alcohol. So what ethanol, ethanol is it's a two-carbon molecule, C1, C2, with an alcohol OH attached to it. So we've taken ethane and added an OH to it, and it's become ethanol. Ethane served as the parent to the molecule ethanol. So that's why we start with alkanes, is because they are the parent and backbone of all of the other molecules we're looking to study. The next molecule is propane. Propane has 3 carbons, so the structure looks like this. Propane, you may have heard that term before. That's the stuff we put in a steel container below grills. So again, we burn it because it burns cleanly and doesn't make a lot of soot, which would be bad for things like the food we're trying to cook. It doesn't smell as bad as methane, and it's not as volatile as methane and ethane, so you can contain it safely within a stainless steel container. Okay, the next molecule up with 4 carbons is butane. So butane has a structure like this. It has 4 carbons now. And I could write the formula next to each of these. C3H8, C4H10. So butane, you may have heard before. Butane is the stuff we put in little lighters that people used to use frequently for smoking cigarettes and that sort of thing. And you put them in these little plastic lighters. So butane, if propane was safe to contain, but we still had to contain it within stainless steel, butane is even safer to contain. It actually stores conveniently as a liquid, but evaporates easy enough for us to spark and light it as a flammable liquid. And again, it burns clean. Could you imagine if you flicked open a lighter and there would be a bunch of smoke and ash? That would not be super convenient, making smoking even less healthy than it already is. You know, these days though, fortunately, people don't usually carry those lighters around because they're not lighting cigarettes as often anymore. Instead, they're using those little kind of butane guns to light candles on a birthday cake or something. So maybe that'll be the analogy that people relate to in the future. One can only hope. Okay, so we've done methane with 1 carbon, ethane with 2, propane with 3, and butane with 4. Now, from 5 to 10, it actually gets a little bit more intuitive as the names start to sound like things you've heard before. So 5 is going to be pentane, pent, like pentagon. Pentane 6 is going to be hexane. There is no sexane. And then 7 is going to be heptane. 8 is octane. 9 is nonane. And 10 is decane. So now the numbers start to at least sound like the numbers that they're relating to. So pentane is 5 carbons, hexane is 6 carbons, heptane is 7 carbons, octane is 8 carbons, nonane is 9 carbons, decane is 10 carbons. So each of these chains just gets longer and longer. Just a quick tip, if you're drawing a long straight chain alkane, if you start and end on kind of the same part of the molecule, you have an odd number of carbons, just a pro tip. Whereas if you start down and end up or vice versa, you have an even number of carbons. But one could always just count 1, 2, 3, 4, 5, 6, 7, 8 to check that they do indeed have 8 carbons on their octane molecule. So these are the fundamental hydrocarbons, and they're going to be very important for allowing us to kind of see and build more complicated molecules. And so what I want to do now is move into kind of other aspects of these hydrocarbons. And the first is determining the formula of a hydrocarbon. So if you have some alkane, the molecular formula is going to be CnH2n plus 2. So for example, in heptane, we had N is equal to 7 because we had 7 times carbon for our heptane molecule. So our formula is then C7H. If you look, it's going to be 2 times 7 plus 2, which is equal to 16. Is that what I had on the other page here? Oh, I didn't write it out. Well, so 16. Let's check that. There's hexane, heptane. So we have 7 carbons, 3 hydrogens here, 2, 2, 2, 2, 2, 3, 6 plus 10 is 16 hydrogen atoms. Okay. So that works, but there's also rings. So for rings, the formula is C2N, CnH2n. So you just remove the 2. So for example, in this molecule, we have 1, 2, 3, 4, 5, 6. We have C6, and then we have 2 H's at every position. So it's 2 times 6, which is just 12, C6H12. So it's, those are 2 formulae that I felt like I should share with you. I use them sometimes, like when I need to really quickly get a student the formula, but rarely are people in a position where they need the formula so quick that they can't just draw the structure and count carbons and hydrogens. But it never hurts to know these things. You can always check your answer. A key insight, though, when you look at the ring structures, is rings are going to lose that +2 because they don't have the CH3 end caps. Now, speaking of rings, so what about rings? Are rings alkanes? That is to say, this is hexane. So what about this molecule, which has 6 carbon atoms, but the ends are connected in a ring? That molecule is called cyclohexane. And so if an alkane is connected on either side, it's a ring structure. So alkanes can be rings. Alkanes can be rings. And those cyclic alkanes are called cycloalkanes. So when we form molecular rings, we call them cyclic molecules. So cycloalkanes are a class of cyclic molecules. So what am I getting at? Well, you could have cyclopropane with 3 carbon atoms. Maybe I'll write it this way. 3 times C. You could have a square for cyclobutane. You could have a pentagon for cyclopentane. Now let's go back before we go too big with our shapes. What's nice is everything's fairly intuitive so far. If we've got a 3-sided cyclic molecule, it's a triangle, and that works for the most part. Okay, what about 2 times C and 1 times C? There is no cyclomethane, there is no cycloethane. You cannot have one side on a shape, okay? So there we go. I mean, maybe a circle would technically have one side, but no. There is only methane, there's no cyclomethane, and there's no cycloethane. Some have argued that a carbon-carbon double bond is the smallest ring, as it's a 2-sided ring, but I'll just chalk that up as a different functional group that we'll look at in the future. So we have cyclopentane, butane, and propane. And we could keep getting bigger. I did mention cyclohexane on the previous page. And that's usually where I stop on exams, because as I get to the more complicated shapes, students, 1 year on a really hard exam, I put a question where students had to draw multiple heptagons, and they were not happy with me. So I pay attention to student feedback. But that doesn't mean I shouldn't show it to you now. So here's cycloheptane, 7-sided shape. If you practice it, you will get good and fast at it. It's just one of those things, do I really want to practice drawing a heptagon? We'll get plenty of practice drawing a hexagon in this class. That's been the joke of organic chemistry, but you know, there's good reason for that. All right, now I'm going to try to show off here. Did I hit 9 sides? 1, 2, 3, 4, 5, 6, 7, 8, 9. Whew, did it. Cyclononane, and I'm not going to give cyclodecane a try. You get the idea, hopefully. So again, what are you probably going to have to draw for me? It's cyclopropane, butane, pentane, and hexane. Hexane definitely. We'll look a lot at hexane, especially on the next module. So that's kind of the cyclic molecules and their various fundamental names. So that was the first look at alkane structure and the various parent molecules. Again, commit those to memory. The ones you're really going to have to work on are methane, ethane, propane, and butane. Know them, know them, know them.